time travel is real? It's happening right now in your pocket as you watch this. Every GPS satellite orbiting above you is traveling through time. Every astronaut who returns from space has aged slower than you. Every particle accelerated in a laboratory proves that time itself can be stretched, compressed, manipulated. This isn't science fiction. This is science fact. But how did we discover this impossible truth? How did a patent clerk in Switzerland realize that time wasn't what we thought it was? Let me tell you a story that will change everything you believe about reality. My name is Albert Einstein, and in 1905 I destroyed time itself. I was sitting in my office in Bern, struggling with a problem that had been haunting me for years. Light. What is light really? Is it a wave? A particle? And if it's a wave, what is it waving through? Scientists called it a luminiferous ether, an invisible substance that filled all of space. But every experiment to detect this ether failed. It was as if it didn't exist. Then came the strangest discovery of all. No matter how fast you moved, no matter what direction you traveled, light always moved at the same speed. Always. 299,792,580 meters per second. Never faster, never slower. This made no sense. Think about it. If you're on a train moving forward at 60 miles per hour and you throw a ball forward at 20 miles per hour, that ball is moving 80 miles per hour relative to the ground. Addition. Simple math. But light doesn't obey this rule. Shine a flashlight forward from that moving train, and the light still travels at exactly the speed of light. Not the speed of light, plus the speed of the train. Just the speed of light. This obsessed me. I would lie awake at night, imagining myself riding alongside a beam of light. What would I see? According to everything we knew about physics, if I could travel at the speed of light, that light beam should appear stationary beside me. But light can't be stationary. Light is oscillation, vibration, wave motion. A frozen wave is impossible. This impossible thought experiment led me to an earth-shattering realization. The problem wasn't with light. The problem was with our understanding of space and time. We assume time is absolute, that there's one cosmic clock ticking the same for everyone in the universe. 1 second here equals 1 second on Mars equals 1 second at the center of the galaxy. But what if that's wrong? What if time isn't the same everywhere? I realized something that seems impossible but must be true. Time slows down when you move fast, not because of some mechanical effect, but because time itself is flexible. Moving clocks run slower. Not broken clocks, all clocks, including biological ones, including you. Picture this. You're standing on a platform watching a train speed by. On that train, someone turns on a flashlight. The light travels forward through the train car, hits a mirror at the front, and reflects back. Simple. But here's what breaks your mind. From your perspective on the platform, that light has to travel a longer path. Why? Because while the light is traveling forward and back inside the train, the entire train is moving. So from your view, the light follows a zigzag path, forward and sideways with the train, then back and sideways with the train. Longer path, same speed of light. What does that mean? It means the light takes more time to make the round trip from your perspective than from the train passenger's perspective. But here's the crucial point. Both observers must agree about the speed of light. It's always the same, exactly. 299,720,58 meters per second. The only way this works is if time itself runs differently for the moving observer. Time must slow down on the train. Not by much at everyday speeds, but measurably, predictably, inevitably. This is time dilation, and it's not theory anymore. We've tested it thousands of times. In 1971, physicists Eiffel and Keating took atomic clocks on airplanes, flying them around the world. When they landed, those airborne clocks were running slower than identical clocks that stayed on the ground. The difference? Nanosecond. Tiny, but exactly what my equations predict. But the real proof is above your head right now. GPS satellite. These satellites orbit Earth at about 12,500 miles per hour, roughly 8,700 miles above the surface. At that speed, time runs slower for them than for us down here. How much slower? About 7 microseconds per day. 7 millionths of a second. That doesn't sound like much, does it? But GPS works by measuring the time it takes signals to travel from satellites to your phone. Your phone calculates your position by comparing arrival times from multiple satellites. If those satellite clocks were off by even microseconds, your GPS would be wrong by miles. So engineers had to account for time dilation. They programmed the GPS satellites to run their clocks slightly fast to compensate for time running slower due to their motion. Without this correction, GPS would be useless. Every smartphone in your pocket is proof that time travel is real. But wait, there's more. Gravity also affects time. The stronger the gravitational field, the slower time moves. This is even stranger than motion affecting time, but it's equally real and equally measured. GPS satellites don't just move fast, they're also farther from Earth's center, where gravity is weaker. Weaker gravity means time runs faster up there. This gravitational effect partially cancels the motion effect, but not completely. The satellite's clocks still need adjustment. How did I know gravity affects time? It came from another impossible thought experiment. Imagine you're in an elevator with no windows. The elevator starts accelerating upward. You feel pressed against the floor. Now imagine instead that you're in the same elevator, but it's sitting on the surface of a planet with strong gravity. You feel pressed against the floor in exactly the same way. Here's the key insight. You cannot tell the difference between acceleration and gravity. They're equivalent. If acceleration affects time, which it must, because acceleration involves motion, then gravity must also affect time. This means time runs slower on Earth's surface than in space. Clocks at sea level tick slower than clocks on mountain tops. The difference is tiny, about 3 parts in 10^16 for every meter of height, but it's measurable with precise atomic clocks. In 2010, physicists at the National Institute of Standards and Technology measured this effect over a height difference of just 33 centimeters, about 1 foot. They confirmed that time runs measurably slower at the lower position, 1 foot closer to Earth's center, and time itself changes. This isn't just academic curiosity, this is fundamental reality. Time is not absolute. Time is not the same everywhere. Time depends on motion and gravity. But here's what really breaks your brain. From your own perspective, time never seems to change. If you're moving fast or in a strong gravitational field, your clocks don't appear to run slow to you. Your biological processes don't seem slower. Everything seems normal from your reference frame. It's only when you compare with someone else that the difference appears. The moving person ages slower compared to the stationary person. The person in stronger gravity ages slower compared to the person in weaker gravity. This leads to real-time travel paradoxes that actually happen, not science fiction. Documented reality. Consider the twin paradox. You have identical twins. One stays on Earth. The other travels to a nearby star at very high speed, close to the speed of light. When the traveling twin returns, she's younger than her earthbound sister. How much younger depends on how fast and how far she traveled. This isn't speculation. Particle physicists observe this constantly. Unstable particles called muons are created when cosmic rays hit our atmosphere. These muons decay very quickly. Their average lifetime is about 2 microseconds. At the speed of light, they should only travel about 600 meters before decaying. But we detect muons at Earth's surface, 10 kilometers below where they're created. How is this possible? Time dilation. The muons are traveling so fast that time slows down for them. From our perspective, they live longer because their internal clocks are running slower. From their perspective, their lifetime is normal. But the distance to Earth's surface is compressed due to length contraction, another consequence of relativity. Either way you look at it, muons created in the upper atmosphere reach the ground because of time dilation. Every cosmic ray detector on Earth proves time travel is real. The faster you move, the more dramatic the effect becomes. At 90% the speed of light, time slows down by a factor of 2, 3. At 99%, it slows down by a factor of 7. At 99.9% by a factor of 22. As you approach the speed of light, time dilation approaches infinity. This is why we can never reach the speed of light if we have mass. Time would stop completely from the outside perspective. From your perspective, you'd need infinite energy to accelerate further. But here's the strangest part of all. Light itself experiences no time. From a photon's perspective, if photons could have perspective, the entire journey from emission to absorption happens instantaneously. A photon traveling for billions of years across the universe experiences no time passage. For light, the universe is collapsed to zero thickness. All of space is one instant. This reveals something profound about the structure of reality. Space and time aren't separate. They're woven together into space-time, a four-dimensional fabric that can be stretched, compressed, warped, twisted. Massive objects warp the space-time fabric. The more massive an object, the more it warps space-time around it. We experience this warping as gravity, but the warping also affects time. Time runs slower in warped regions of space-time. Near a black hole, this effect becomes extreme. Close to the event horizon, time dilation can be enormous. Fall toward the black hole, and from the outside perspective, you appear to slow down, freeze, and fade away at the event horizon. But from your perspective, you fall right through in normal time. This isn't just theory. We've observed this effect around real black holes. We've watched matter spiral into black holes and seen it appear to slow and stop at the event horizon. Exactly as predicted, the universe is far stranger than our everyday intuition suggests. Time isn't a river flowing at constant rate. It's a dimension that can be manipulated, stretched, compressed. Every GPS satellite, every particle accelerator, every precise clock proves this daily. We live in a universe where time travel is not only possible but mandatory. Every time you move, you travel through time at a slightly different rate than someone standing still. Every time you climb stairs, you enter a region where time moves slightly fast. Every time you use GPS, you rely on technology that compensates for time travel effect. The patent clerk who imagined riding alongside light beams discovered that our most basic assumptions about reality were wrong. Time isn't absolute. Space isn't separate from time. The speed of light isn't just a speed limit, it's the rate at which cause and effect propagate through space-time itself. And this discovery opened the door to technologies we now take for granted. GPS navigation, particle accelerators, precision timekeeping, space travel, all depend on understanding time dilation. Without relativistic corrections, none of these work properly. So the next time you check your phone's location, remember, you're holding proof that time travel is real. You're holding evidence that a young man's impossible thought experiment about riding light beams revealed the deepest secret of the universe. But here's where it gets truly mind-bending. What I discovered about time led to something even more impossible. The realization that past, present, and future might all exist simultaneously. Think about what time dilation really means. When you travel fast, time slows down for you relative to everyone else, but from your perspective, it's everyone else whose time speeds up. There's no absolute now that everyone agrees on. Your now is different from someone moving relative to you. This destroys the idea of simultaneous. Events that are simultaneous for you might not be simultaneous for someone else. The universe doesn't have a single, universal present moment. Instead, different observers slice spacetime into different present moments. This leads to something physicists call the block universe. Past, present, and future all exist equally. You think the past is gone and the future hasn't happened yet, but that's just your perspective sliding along your particular slice through space-time. From a broader view outside of time, everything that ever was or will be exists simultaneously. I struggled with this implication. It seems to destroy free will. If the future already exists, are our choices predetermined? I never found a satisfactory answer to this question. The mathematics is clear, but the philosophical implications remain disturbing. But let's return to something more concrete. The practical reality of time travel that's happening around us every day. Do you realize that atomic clocks at different altitudes on Earth run at measurably different rates? The atomic clock at the National Institute of Standards and Technology in Boulder, Colorado, sits at 5,430 feet above sea level. Compared to an identical clock at sea level, it gains about 5 nanoseconds per day due to gravitational time dilation. 5 nanoseconds might seem insignificant, but it's not. The global positioning system requires time synchronization accurate to within 20 to 30 nanoseconds, without accounting for both gravitational and motional time dilation. GPS errors would accumulate at about 10 kilometers per day. Within hours, your navigation would be completely useless. This forces us to live in my relativistic universe every single day. The engineers who designed GPS satellites had to program them to run their clocks 38 microseconds per day fast to compensate for time dilation effect. They had to apply corrections that most people consider impossible fantasy. Even more remarkably, we can see time dilation effects in biological systems. In the 1970s, scientists placed identical populations of bacteria on high-speed centrifuges, subjecting them to acceleration for extended periods. The accelerated bacteria aged slower, they underwent fewer generations and accumulated fewer mutations than control populations. Life itself experiences time dilation. Every cell division, every molecular reaction, every biological process slows down in accelerated reference frames. This isn't just physics, it's biology, chemistry, the fundamental rate at which reality unfolds. Now consider what this means for space travel. If humans ever journey to nearby stars, they'll experience dramatic time dilation effect. A trip to Proxima Centauri at 90% light speed would take about 7 years from the traveler's perspective, but over 10 years would pass on Earth due to time dilation. The travelers would return to find everyone they left behind had aged more than twice as much. This isn't science fiction speculation. It's mathematical certainty based on principles we've tested millions of times in laboratories. But here's something even stranger. Time dilation isn't symmetrical in all cases. The classic twin paradox has a resolution that breaks your intuition about relativity. Both twins can claim the other's clocks are running slow while they're separating at constant velocity, but the traveling twin must turn around to come home. During the turnaround, she experiences acceleration, breaking the symmetry. The resolution: she ages less than her earthbound sister. This has been verified using atomic clocks flown in opposite directions around Earth. The universe becomes even stranger when you realize that time dilation affects causality itself. In extreme cases involving objects moving close to light speed, the order of cause and effect can appear different to different observers. This seems impossible, but it's mathematically inevitable if nothing travels faster than light. The speed of light isn't just the speed limit, it's the speed at which causality propagates. It's the ultimate speed of cause and effect. This reveals why faster than light travel would create paradoxes. If you could send information faster than light, you could use time dilation effects to send messages into your own past. You could create grandfather paradoxes with radio waves. The universe seems to protect causality by making faster than light travel impossible. Every time we try to accelerate particles to light speed, they require more and more energy. As they approach light speed, their relativistic mass approaches infinity, requiring infinite energy for that final bit of acceleration. We've tested this countless times in particle accelerators. Electrons, protons, heavy ions, they all follow the same rule. The closer to light speed, the more energy required for further acceleration. It's as if the universe has a built-in speed limit to prevent causality paradoxes. But the most mind-bending aspect of time dilation might be this: it reveals that time itself is an emergent property of space-time geometry. Time doesn't flow in some absolute sense. Instead, time is the dimension along which entropy increases, along which cause leads to effect. In regions of strong gravitational fields, where space-time is heavily warped, this temporal dimension stretches. Time dilates because space-time itself is distorted. You're not just moving through time differently. The very structure of temporal reality around you has changed. This connects time dilation to the deepest mysteries of physics. Why does time seem to flow forward? Why do we remember the past but not the future? Why does cause precede effect? All of these questions relate to the structure of space-time and the relationship between geometry and time. Near black holes, these effects become extreme enough to challenge our understanding of time itself. At the event horizon, time dilation becomes infinite. From an outside observer's perspective, time appears to stop completely. But from the perspective of someone falling in, time continues normally, even as they pass beyond a point of no return. This suggests something profound. Time isn't fundamental. Time might be an emergent property of more basic physical laws. Just as temperature emerges from molecular motion, time might emerge from the geometry of space-time itself. Every GPS satellite, every atomic clock, every particle accelerator is a window into this deeper reality. They're all proof that our common sense understanding of time is fundamentally wrong. They're all evidence that we live in a universe far stranger and more wonderful than our ancestors could have imagined. The next time you use GPS navigation, remember this: you're not just finding your location. You're participating in a daily demonstration that time itself is malleable, that the universe operates according to principles that seem impossible but are absolutely, measurably, undeniably real. Time travel isn't science fiction, it's science fact. And every second of every day, we're all traveling through time at slightly different rate, proving that the universe is far more mysterious and beautiful than we ever dared to dream. Time isn't what you think it is, and that changes everything.